So instrument type and location, right? You see all these basic shapes accessible to the operator, mounted in the field, and not normally accessible. So these are examples of how they show them, right? Solid line, no line, dash lines. So the symbols stay the same, but then you just put no line, dash lines, or regular lines in them. Okay, straightforward. Transmitter symbols. So orifice meter, an example of an orifice meter, a turbine meter, and an undefined meter, right? So these symbols are just going to tell you, okay, this transmitter, this is how we expect them to look like. Then the abbreviations is the more important thing, right? We just saw one that says FT, right? Flow transmitters. So if you want to know and distinguish the type of transmitter, then you have to now look for the symbol. PNIDs can be a headache sometimes, but I'm sure that some of you may be working with it. Anybody in this class that work with PNIDs on a daily basis? I mean, if any of you do, then I'm sure this class is really boring to you, right? Because you know everything already. So just bear with us, okay? While we try to catch up to speed to you. All right. But yeah, once you work with PNIDs every day, then it just helps you, like you just keep knowing what it means and all that stuff. Okay. So I see Alice has worked with PNIDs. So instrumentation abbreviations. I do know that even though you work with sometimes you may not be used to seeing some other ones because your facility doesn't use them. But I'm sure that you would have an inkling. Your experience would help you see, okay, since this means this for this, then probably it means this for that. So set points, usually abbreviated by SP. Everybody knows what fail close means. You've seen fail close, feedback, and all these symbols. I think going to the exam, you probably need to know all these by heart. Like you don't want to be searching for what normally closed means, normally closed valve means. Like you want to look through those and know those. When a valve is locked open or is locked closed, right? Those are symbols that we use on the field when we go to inspect those valves and we want to do compliance report for the client, right? We just go out there and say, okay, the tags that are given on those valves, locked open, locked closed, are they really what is shown on there? Okay. So these symbols are important. So that's why we put them here to emphasize them. Okay. Miscellaneous symbols. These ones are actually more fun because they're actually a little bit intuitive. Tanks, mixers, towers with packing. So if we have seen all these PFDs or block diagrams in the past, we would have actually picked up on all these ones. The furnace is pretty intuitive, right? Right? Okay. So scale ups. Yeah, I think we have a short problem on this scale up, but scale up is a very important concept. In chemical engineering, personally, people have classed this topic under similitude concepts. Basically, we want to scale up. Scale up is something that most plants actually do in their inception phase, right? They have a pilot plant, as you see in this diagram, right? I mean, not necessarily in a laboratory, but they kind of design the process and then they make a pilot plant of it, and then they scale up to a demonstration of it, and then before they make it commercial, they've tested controls, they've tested throughputs, they've tested process conditions, pressure, temperatures, how things are interconnected before they now go to the commercialization phase. But to do all these 3 steps, you have to make sure that the model and your full scale unit, they go through 3 different similarities, right? They must be geometrically similar, they must be kinematically similar, and then they must be dynamically similar, right? We all know that geometric means that in terms of the shape, right? We want the shapes of those things to look similar, or at least go with a ratio. So the ratio of the components must be similar. Remember we talked about capacity earlier, capacity indices and stuff. So we cannot, if we're going to scale up, we have to scale up appropriately based on how each unit operates. And then if it's just a size thing like the turbine blade, we have to scale up with geometry. Kinematic, if you remember, means something that is velocity. It has to do with velocities, right? The velocities must scale up also as well. And then the last one is dynamic similarity. Okay? So the damp color number is the dimensionless number that is used if there's a chemical reaction time scale that we have to accommodate for. Okay, so when you're doing scale ups, like I said earlier, you're not going to only rely on the chemical engineer. You have to work with other engineering guys to see how the scale up is going to affect their own process.